Welcome once again. In this session, we are going to discuss Nyquist criteria for distortionless transmission. As we know that in baseband transmission of digital data, the sampled output yi is mu times of ai, which means that ith transmitted bit is decoded correctly in absence of inter-symbol interference. That is called distortionless transmission of digital data. In order to minimize the effect of ISI, the designing of the transmit filter and receive filter is totally based on the Nyquist criteria. To understand this, we consider output of the overall pulse spectrum, that is called yt, and it is equals to mu times of summation ak p function of t minus ktb, taking limit k equals to minus infinity to plus infinity. Here we assume that the effect of noise is neglected, and the Nyquist criteria is based upon two steps. In step 1, there is a process of sampling, that is called extraction. In this extraction process, the output yt is sampled at t equals to itb and result the sampled output yi. Then decoding is performed in the second step. Here the weighted pulse is obtained, that is free from inter-symbol interference, and obtained at I equals to k. This weighted pulse is represented by ak p function of itb minus ktb. Here when we put I equals to k, we get ai p function 0, that is equals to ai, since the normalization of pulse pt is equals to 1. So after performing extraction and decoding, the pulse p function of itb minus ktb is equals to 1 for I equals to k. That is the case for free inter-symbol interference, and it is equals to 0 for I not equals to k. Here for I equals to k, the p function 0 is equals to 1, that is due to normalization. And when the received pulse pt satisfying this above condition, then only we get the receiver output yi equals to mu times of ai. That is called distortionless transmission having 0 inter-symbol interference. Now let us discuss the Nyquist criteria in brief that include extraction and decoding process. For this, we consider received pulse pt sampled at t equals to mtb and produce a sampled signal p del t. For sampling process, we consider a periodic train of pulse denoted by s del t, that is equals to summation del t minus mtb, taking limit m equals to minus infinity to plus infinity. In sampling process, the sampled signal p del t is simply the product of input pulse pt and periodic train of pulse s del t, that is in time domain. For frequency domain, we use Fourier transform. Here p function f is Fourier transform of pt, s del f is the Fourier transform of s del t, and p del f is the Fourier transform of p del t. Now this sampled signal p del t can be written as summation p function mtb del t minus mtb, taking limit m equals to minus infinity to infinity. Here p function mtb is the sampled version of received pulse p function t. Now taking Fourier transform of p del t represented by p del f, and it is equals to integration p del t e to power minus j 2 pi ft into dt, taking limit t equals to minus infinity to plus infinity. In place of p del t, we can write summation p function mtb del t minus mtb, taking limit m equals to minus infinity to plus infinity. Next, we assume that m equals to I minus k in order to define our Nyquist criteria. After putting I minus k in place of m, we get p del f equals to integration within bracket summation p function I minus k into tb del t minus I minus k tb e to power minus j 2 pi ft dt. Now From this, we consider a pulse p I minus k into tb, and its value is 1 for I equals to k, since p function 0 is equals to 1 after normalization, and 0 for I not equals to k. And this is a condition for distortionless transmission. So p del f equals to integration p function 0 del t e to power minus j2 pi ft into dt when I is equals to k, and 0 when I is not equals to k. Now for Nyquist criteria for distortionless transmission, we consider case for I equals to k. When I equals to k, p del f equals to p function 0 integration del t e to power minus j2 pi ft into dt. Here the integration term is simply the Fourier transform of del t, and the Fourier transform of del t is equals to 1. So p del f equals to p0 for I equals to k, and it get converted into 1 after normalization. And it is confirmed that the received pulse is normalized for I equals to k, and in this condition the transmitted bit is encoded correctly. Next, we derive a relation of pulse shaping function pt, which satisfying this condition called Nyquist criteria for distortionless baseband transmission having zero intersymbol interference. For this, we again use sampled pulse p del t, that is equal to product of p function t and s del t. Now taking Fourier transform on both sides, and we get p del f equals to pf convolution s del f. Here we use a property of Fourier transform that is called convolution in frequency domain, which states that the convolution in frequency domain is the result of multiplication of corresponding function in time domain. Here S del f is the Fourier transform of periodic train of pulse, and it is equals to fs summation del f minus n fs, taking limit n equals to minus infinity to plus infinity. Now for our convenience, we can write fs equals to 1 upon tb, that is called bit rate, denoted by r suffix b. So p del f is equals to pf convolution rb summation del f minus n rb. To solve this relation, we use the convolution property of impulse function. Here the impulse function is the shifted function delayed by n rb, and rb is the constant that is called bit rate. So the convolution of pf and del f minus n rb is equals to p function f minus n rb. Also, using the definition of Fourier transform, the Fourier transform of p del t is p del f, that is equals to integration p del t e to power minus j2 pi ft into dt. In place of p del t, we can write pt into s del t. And after sampling at t equals to mtb, the Fourier transform becomes p del f equals to integration within brackets summation p function mtb del t minus mtb e to power minus j2 pi ft into dt. Here the limit of summation is m equals to minus infinity to plus infinity, and outside the bracket there is an integration whose limit is t equals to minus infinity to plus infinity. And here we consider only the received pulse p function mtb. And after assuming and putting m equals to I minus k, we get p function I minus k into tb, that is equals to 1 when m equals to 0 and 0 when m is not equals to 0. Here m equals to I minus k. The value of 1 is obtained after normalization, that is p function 0 equals to 1 for I equals to k, and value 0 is obtained for I not equals to k. Again, for the Nyquist criteria for distortionless transmission, we consider I equals to k or m equals to 0. And we get m del f equals to integration p function 0 del t e to power minus j2 pi ft into dt. Here the value of impulse function del t equals to 1 for t equals to 0 and 0 for t not equals to 0. So we put del t equals to 1 for t equals to 0 and we get p del f equals to p function 0 and it is equals to 1. Also in place of p del f we can write rb summation p f minus nrb taking limit n equals to minus infinity to plus infinity. That we have derived in terms of bit rate, that is called r suffix b. And from this we can derive a relation of pulse shaping function pt which satisfying the condition of Nyquist criteria having zero intersymbol interference, and this relation is summation p f minus nrb equals to 1 upon rb. Here pulse shaping function pt having a Fourier transform p function f, and this satisfies a relation called 1 upon rb, and this relation is obtained after taking a condition of p itb minus kdb equals to 1 for I equals to k and 0 for I not equals to k, and this condition is called Nyquist criteria for distortionless baseband transmission having zero intersymbol interference.